So you've made a lot of arguments in favor of inflationary models and in favor of comparing, in fact, it's theory comparison between these inflationary models and alternative possible explanations of what we observe. As we go into the era of what we now call precision cosmology and make more and more observations, what do you see as being future tests of inflation and the future status of the theory?
So I think that the search for B-mode polarization in the microwave background is crucial, because this is a test with which we can distinguish good inflationary models from some of the alternatives. I think looking at new observation windows like 21 centimeter redshift surveys will also teach us something. It will probably teach us more about primordial non-Gaussianities. Then it probably won't teach us about inflation versus alternatives, but primordial non-Gaussianities might distinguish between inflationary models. So I think the future is bright on the observational side. I would actually like to see some observation coming in with a completely unexpected result that would force theorists to go back to the drawing board. Because if you look at what cosmology theorists are doing now in 2017, they are using the same tools that they were using in 1980. And although in 1980 these tools were very powerful, they made predictions, we developed completely new insights into the early universe evolution. These tools have not allowed us to address the cosmological constant problem. They've not really allowed us to gain any insight on dark energy. And so I think we need some kind of new data that will shake things up. And maybe this new data will come from observations of the redshift dependence of dark energy. Maybe this is where the standard paradigm of cosmology will fail. And in light of this happening, I think we need to keep working on alternatives, even if eventually inflation turns out to be right. Because so if there are students listening to this, then maybe a student should come away from this discussion with the idea that inflation has been extremely successful, that it is maybe the most self-consistent theory of the very early universe, compared to its competitors like string gas cosmology, the matter balance, the ekpyrotic scenario. But self-consistent doesn't necessarily mean consistent. Okay. And so one should keep the eyes open. Maybe students will be able to develop alternatives into things which are, into models which are not only self-consistent, but also consistent with fundamental physics.
So ultimately, you'd like to see this sort of connect on two ends then, right? You'd like to see further observations, which in some sense are either testing to destruction or to confirm the theory. But also you'd like to see it embedded on the theoretical end at a much sort of higher level. You'd like to see this descend from, in your case, a string theory or some sort of theory of everything.
Because I really would like to see cosmological observations emerge as a robust window to probe fundamental physics. Fundamental physics at the highest energy scales, at the energy scales where we probe quantum gravity. I think we already see that this is the direction things will head, but we need to be more quantitative.
So on that question though, is not inflation a bit of a problem for us in this sense, in the sense that if quantum gravity happens at, for example, the Planck scale, and this is followed by a period of inflation, would not any signature of this quantum gravity just be washed away by the overwhelming inflationary effects?
I believe the answer is no. And the reason that I gave this answer is the following. If you assume that there was a long period of inflation, then if you trace back the length scales that we observe today, we trace them back to the very early universe, then the physical length of those scales is much, much smaller than the Planck length. So there's a problem, an issue, which we call the trans-Planckian problem for cosmological fluctuations. And from a point of view of quantum gravity, this is the trans-Planckian window of opportunity. So my view is that you have an early universe inflationary period, which you can visualize as some soup, high-density soup, on length scales smaller than the Planck length. Quantum gravity is operative, and this soup will be vibrating, and it's quantum gravity that imprints the fluctuations, which will then redshift, the lengths will expand, and the imprints will survive to be measured today.
So I guess your perspective would be that the largest amounts of inflation, so the largest scales that we see, are either trans-Planckian in the sense that if we have more than 70 or 80 e-foldings of inflation, that these scales should have been sub-Planckian when they originated.
Right.
Or that it should be a window because there wasn't sufficient inflation to wipe out any primordial quantum gravitational effects.
Yes.
And so you would sort of advise anyone working on quantum gravity to either look at how a quantum gravitational fluctuation can become one of these long-range modes?
Yes. So if you work on quantum gravity, then I think you have a golden window of opportunity to test the theory with observations. But you have to look into this window both from the point of view of inflation and from the point of view of alternatives.
Thank you.
Thank you.